Dr. Debashis Khan received his PhD degree in mechanical engineering from the Indian Institute of Technology, Kharagpur in 2007. He's an associate professor in the Department of Mechanical Engineering at the Indian Institute of Technology, Varanasi. His research interests include analytical and computational methods in science and engineering, solid mechanics, fracture mechanics, continuum mechanics, and finite deformation plasticity. He's a member of the American Society of Mechanical Engineers, the Indian Society for Theoretical and Applied Mechanics, and a fellow of the Institution of Engineers India. He was a visiting research scientist at the Department of Material Science and Engineering at the University of Texas, North Texas actually, in USA, and the Zernike Institute of Advanced Materials at the University of Groningen in the Netherlands, Holland. He has since worked with Professor Ellen Needleman, a stalwart in the area of computational fracture mechanics, and Professor Eric van der Giesen, a stalwart in the field of computational mechanics too. He has published numerous peer-reviewed papers in international journals of repute and many conference papers. He has recently co-authored a popular book entitled Mathematical Theory of Subdivision, Finite Elements, and Wavelet Methods. He has a keen interest in mathematical formulation of evolutionary systems and their exploration in the origin of life, which led him to work on the interface of science and spirituality in collaboration with the Bhaktivedanta Institute. So without further ado, I'd like to hand over the screen to Dr. Debashis Khan. Sir.
So my topic of presentation is mathematical basis of Darwin's natural selection theory. Okay. So mainly I will be dealing with mathematics and theory of evolution by Charles Darwin. Okay. So before starting my actual presentation, let me look into this line. Why did I select this topic? For most of the great scientists, the quest for life started out of their tremendous research, okay, in the academic area. But for me, it is not like that because I am not so big scientist. But my quest for this topic or the origin of life started from the point that why do we suffer? Okay? So our suffering may be on individual ground, on community ground, or worldwide problems like this COVID-19. Okay, so even though there are solutions like this temporal solutions or like short-time solution, long-time solution for some of our problems, but I was looking for, is there any permanent solution to mitigate our suffering or to end our suffering? And in that journey, I came to this point, this theory of evolution or this origin of life. In fact, so there are several approaches in order to target the solution for this topic or to come out from the confusion. So there are several approaches, like people started to explore this matter on the basis of the knowledge of physics, knowledge of chemistry, okay. But the problem is that in physics, in chemistry, so the experimentation involved is too much, okay. And everybody or means every country, every nation even cannot, okay, spend that amount of money to explore such kind of tremendous experimentation, okay. And the remaining hope is that we have the tool like mathematics, okay. So the mathematics actually is a wonderful subject, okay. So the in pure math, so because in mathematics only we can have perfect knowledge, and this pure mathematics is based on perfect knowledge. So whenever we are unable to do the tremendous experimentations, okay, in order to target the solution of this foundational problem like life's origin. So if we can develop some logic, and if that logic is very perfect, we can also have the solution of this problem of life's origin. And in fact, our tour, Professor Tour, towards the end of his lecture, he hinted of this mathematical roots. Okay, so I appreciate that, because in absence of this tremendous experimentations, the mathematical approach is the only way we are having in order to come out of this situation, or in order to solve this problem. Of course, this mathematics is also not very simple, but there are the mathematics is also we have pure mathematics, applied mathematics, and in the applied mathematics there are simulations, but in simulations also there are several idealizations or assumptions, but the pure mathematics, it is based on perfect logic, and once anything is based on perfect logic, it will give you the perfect answer. Okay, but this pure mathematics is also very difficult subject, but this numerical techniques which are relatively simple, but here again there are several assumptions. So if we, but some guidelines or some idea at least we can get, like in one of the lectures, I think this was asked from the audience side, that how to reduce this time gap, or this those who are supporters of this evolution theory, Darwin's evolution theory, they claim that after sufficiently long time. But what is that time? If that time is very big, then okay, so we cannot do the experimentation and the use of super catalyst. So till now it is of course not available, as I have heard. But even computationally, if we can develop, so in that case also till now we don't have such sophisticated numerical computation technique that which can simulate this super catalyst, because this is one very big point, that time factor. Okay, so with this my actually quest for life started, and that at the beginning I just wanted to tell you. So so in the theory of evolution, the present theories of evolution, we have this natural selection theory and the OS species change, or this new Darwinism. So most of us we know about this, but let me go through in a systematic way, so that as I have a model on the basis of Heidfels mathematical theory of this evolution, so therefore every steps are very very important. So even the evolution, actually one has to look into all the small steps in order to make the model. Otherwise this modeling will not be good, and it will not give you correct result. So in current theory on evolution, these two are very much established, or in fact these are so much penetrated in our academic system that we cannot, these people in general cannot think to rule out from their academic system. So natural selection theory, it is also known as survival of the fittest, where the heritable traits become more common in a population, whereas harmful traits become rarer. And the way of species change, it was originally based on morphology, but now it is based on random mutations of DNA. So the steps involved are, the mechanism involves genetic drift, that small amount of variation, the changes produced in any one generation by drift and selection are small, their differences accumulate with each subsequent generation, and over large time substantial changes in the organism occur, and this process can culminate in the emergence of new species, that is all known species are descendant from a common ancestor through this process of gradual divergence. So the theory of evolution has inspired many people from different areas like biologists, geneticists, physicists, okay, and the also mathematicians, of course. The origin of life is a necessary precursor for biological evolution. Okay. So the current scientific consensus is that the complex biochemistry that makes life came from simpler chemical reactions, but it is unclear how this occurred. And over the time, various models have been proposed for understanding how life may have generated from chemicals on Earth, such as, so this was mentioned by the earlier presenter speakers. So, but just let me go through that. Poprin's model of Covet's Fox model of proteinoid microspheres, Crane Smith's model of clay, Christian de Duves Theostar model, Miller's electrical discharge reactions model, then the discovery of double helix model for the structure of DNA based by this Watson and Crick, and then RNA concept by Crick, Carl Schultz, Orgel, okay, and Sidney Altman. Okay, so these are the various models have been proposed on the origin of life over the time period, but of course these are the measures, but others are also there. And as I have told that this evolution theory has also inspired the mathematicians. So the evolution theory has inspired a number of developments in mathematics to model the evolutionary process and to understand some of its most puzzling features. Fred Hoyle is one of the topmost astrophysicists, as it was mentioned by Chandra Vikramasinghe, and Vikramasinghe, the PhD student of Fred Hoyle. So Fred Hoyle published a book, Evolution from Space, 1982. There, it was calculated that the chance of obtaining the required set of enzymes for even the simplest living cell was rare, since the number of atoms in the known universe is infinitesimally tiny in comparison. So Fred Hoyle argued that even a whole universe full of primordial soup would grant little chance to evolutionary processes. So my mathematical model for the evolution will be based on Fred Hoyle theory. Of course, in certain places, I just try to look into how to make it simple so that it is accepted largely. So to the physicist, this theory of evolution, they think that okay, it is simple feedback equation, but to mathematician, it is not simple as such. It is much more complex. So starting from a basic feedback equation and considering a simple parent to offspring model, this work will describe that the modern biological theory of evolution of species is not capable to maintain stable population from generation to generation. And this work also points out that Darwinian natural selection theory is incorrect, but even if you think it's correct, but it is in a very limited sense, and that does not mean that it may be correct. Okay, so I try to move in a very gradual way so that you also can understand, because mostly equations are there, but of course after every step I will try to summarize that what is presented in that part. So in the step one, as natural selection seems to follow the simple feedback mechanism, Fred Hoyle took this basic simple feedback equation dx by dt equal to sx. This simple differential equation where x is considered to be the fraction of some large population that possesses a particular property A. So please, if you are very much attentive, then actually you can understand. Otherwise, if you lose your interest in between, then it will be difficult. So please keep your patience so that you can understand. The remaining fraction 1 minus x possessing a different property small a, and where individuals beings otherwise similar to each other. Okay. So this is the basic equation I have taken in order to model this evolution theory. The basic the population reproduces itself from generation to generation. Okay, I think this I have not mentioned that this model is for asexual reproduction, and if we consider the this is for asexual reproduction, and if we consider a more complex model for this bisexual reproduction, it will be difficult, but okay, it is possible. So the population reproduces itself from generation to generation with the old die to make the wave young, and change occurs so slowly that time can be regarded as a continuous variable, and the average interval between generations taken as time taken as unit. Individuals with the property capital A and small a in a particular generation are considered to produce offspring in the ratio 1 plus small s is to 1 offspring that survive to become reproductive agents in the next generation. Okay, and with s taken as constant, which is independent of the small x and t. Okay, so this s in the equation 1, so it is constant and it is independent of small x and t. So now, if we integrate this equation 1, okay, with the boundary condition x equal to x0 at t equal to 0, we will get this. Actually, sometimes many steps I have skipped because there are many equations involved within that. But in order to keep the final equation, I'm just present. So for x equal to for t at t equal to 0, x is equal to x0, and which will keep the solution of the equation 1 as x equal to x0 e to the power st or exp. So here I have told already that the small s is constant. So for s is greater than 0 with a is a favorable property, x rises to unity in a time span of minus log x0 by s generations. And if x equal to x0 at t equal to 0, the time span would be about 1400 generations, small compared to the intervals involved in biological evolution. Okay, so as the supporters of the Darwin's evolution theory, they suggest that this digit should be much more. For s less than 0, the solution dies away in a time span of order 1 by s generations, and thereby implying that if a is unfavorable, it will be quickly rejected. So this is very simple. And that's why people adopt this very quickly, that if any property is favorable, it will be evolving, and if any property is unfavorable, so it will be rejected. But this is not so simple. If we look into our this the population generation after generation, actually this stability is maintained. But according to this, actually, this is not true, and therefore this is ruled out. That if we take only the survival of the fittest without considering the mutation part, then it is it would be ruled out immediately. Okay. Now let us come to the second part. Okay, of course, before the second part, let us look into some questions. Okay. And which are of course related to this mutation part. What if individuals with a good gene A carry a bad gene B having largest value of S? Okay. Die the bad gene not carry the good one down to disaster? What of the situation that bad mutations must enormously exceed good ones in number? Let us take a first look at the comparative rates at which good and bad mutations are likely to arise? So these are very natural questions. Most mutation, okay, so here some biological parties involved. For those who are from biology background, they understand better. So most mutation consist of a base pair being changed during the copying of DNA, because amino acids are coded for by triplets of base pairs with 64 different triplets available for only 220 amino acids. The genetic code has an approximately 3 to 1 redundancy in it. This can be taken care of to sufficiently accuracy here by letting the third member of each triplet be considered redundant. And in that way, if we set 3 into 10 to the power minus 9 as the change of any particular base pair being miscopied, the chance of any amino acid being changed in the protein to which a gene gives expression is approximately 6 into 10 to the power minus 9. Thus, a protein with about 160 amino acids in its chain would have a chance of 1 part in a million of being miscopied. Again, I'm repeating, those who are with biology background, they understand better, but as in the course of the derivation, this is involved, so I'm telling. So therefore, the essential problem for Darwinian theory is how to cope up with the continuing threat of adverse mutations from the tried problem of only the single mutation given by equation 1, that is dx by dt equal to sx. Supposing a favorable mutation to occur among the avalanche of unfavorable ones, how is the favorable mutation to advance against the downward pressure of the others? Okay, so these are very, very important and genuine questions, but sometimes still people tell that random mutation. So it is very painful. Okay. The reason why most mutations must be bad is, of course, that random changes made to any complex structure lead to many more downward steps in the operating efficiency of the structure than to upward steps. Okay, so this is very, very common. So in any random change, actually there is very little chance for the improvement rather than to go in downward direction. So this is very important question, and how the occasional lucky improvement is to lead to positive evolution is a puzzle that has disturbed many mathematicians. In a parting model or binary fission model, in both of which progeny inherit the genetic structure of a single parent, because I'm speaking about this asexual reproduction system. So the situation appears unpromising. Rare favorable mutations in such models cannot free themselves from the more frequent unfavorable ones, because an offspring to whom a rare favorable mutation occurs is inevitably saddled with all the unfavorable mutations which have afflicted its parental line. So now I am moving further, step 2. So here, in order to have stable population, like in the integration of equation 1, so we have seen that when the property is favorable, so that property will be elevated, or the evolution of that will be there, and finally only those properties will be existing. And if any property is unfavorable, so it will be eliminated from the system. But as I have told that we see in our population generation after generation stable population. Therefore, in order to normalize that equation, so that equation has been modified, and in fact, in place of this 1 plus s is to 1, that ratio of the number, that average number of offspring from an individual possessing gene type A, instead of 1 by s, here it is being considered that it's alpha into 1 plus s, where alpha is the function of the fraction s of the population, okay, compared to alpha. And in that way, we can get this equation 3 with that. And now considering the generation interval as the unit of time, a differential equation for xt can be obtained from the following equation. So x for t plus 1, okay, that generation will be alpha into 1 plus s into xt for t generation. So writing the above equation, so I have to become a little fast because I have to complete also. So writing the above equation in the form x into x t plus 1 equal to xt plus dx by dt. So these equations are simple to understand, and using equation 3. Equation 3 is here. We have for s very less than 1. So this s value generally we consider that like in the range of 0.01. So but okay, here in this model also there are some idealizations that we may have to modify those. So in that therefore we have now the equation for this feedback equation as dx by dt is equal to sx into 1 minus x by 1 plus sx, which is nearly equal to equivalent to this sx into 1 minus x. And for boundary condition s is equal to x0, and if this x0 is very less than 1 at time t equal to 0, the solution, so it is becoming because we are taking considering that for a very small fraction, and this generation interval or the number of generations should be too high. So therefore the solution of 5 is given by this equation x is equal to x0 by x0 plus e to the power minus st. Okay, and now actually in fact you can see the development of the equation as well as the information which we can see in the evolution theory. So features of equation 6. So unlike solution of equation 1 for s greater than 0, x does not increase to unity at as t equal to minus ln by ln x0 by s, but only to half. So this is very interesting point to note, because it is not now leading to 1. So earlier in the simple case, when this stable population was not the stable population from generation to generation, this concept was not putting it in mathematical terms, so this was not possible to obtain. But here actually we can see that it is not leading to 1 but half. According to equation 6, for s greater than 0, x does not increase strictly to unity at any finite time. Okay, good. And property A does not completely fix itself in the species in any finite number of generations, and a residuum of individuals remain with the disadvantageous property. So therefore, we can see that every time some good and some bad properties will be existing simultaneously, not that all the properties are good or every properties are bad. Okay, it is not like that. So somehow this approach is representing our evolution in a better way. Now I will go to step 3, which is far improvement in the model. So where we are considering the fluctuation in the distribution of the mutation rate from upstream to upstream. Okay, in generation to generation, and this is slightly more involved. So according to the above discussion of mutation rates, the number of potential bad mutations is of order 10 to the power 8. So it is the number of sensitive base pairs. Writing n for this number, and for simplicity, take all deleterious mutations to have the same adverse mutation factor s less than 0. Also take the probability of each bad mutation appearing to be the same as lambda by n, where lambda is equivalent to 0.3 is the total probability per generation of one of the mutations appearing, that is lambda is the average number of bad new mutations appearing as each offspring is born. And this fluctuation given by the Poisson's ratio, so it can be any kind of a distribution, any normal distribution you can take, but here the Poisson distribution has been taken. will evidently occur from offspring to offspring with lambda to the power k to the power minus delta by k factorial. The probability that an offspring is born with k defects. Okay. So therefore here we are considering that from offspring to offspring there are defects, and these defects are also not same for everything, but it is fluctuating. Okay, and this is more a realistic approach, of course. So however, for lambda appreciably less than unity, the Poisson distribution is dominated by k equal to 0 and k equal to 1 with probabilities 1 minus lambda and lambda respectively to the first order in lambda. So this is one case only I am considering in the first order of lambda. So but if we consider the other orders, then the solution will change a bit. So only that one can try. Only these two possibilities are considered in the following equations. So if we consider now that YR, where this R is 0, 1, 2, with the fractions of populations with no defect, with one defect, two defects, in that way up to R defect, and if alpha into 1 minus s to the power R be the number of surviving offspring produced by an individual with R defects. So this is in a model where from generation to generation parents die and are replaced by their offspring, the surviving offspring being those who themselves become parents in the succeeding generation. So which we observe. Then from the definition of the fraction, simply you can write that sum of this YR, where R equal to R is ranging from 0 to R is 1. And for the condition that the population, here again actually that concept that population will be remaining stable from generation after generation. So that concept is being put, and in that way this equation then will be alpha sum of this 1 minus s to the power R multiplied by 1 R, where R equal to 0 to R equal to 1. So now writing the equations which relate to fractions YR from generation to generation with fractions in the t plus 1 generation on the left and fraction in the t generation on the right, we can get these equations. This Y0, as I have told, it is with no defect. Okay, Y1 it is with one defect. So this Y0 t plus 1, it is in the t plus 1 generation, and in the right side it is with the previous generation. So that is alpha into 1 minus lambda into Y0, and for the when the offspring is with one defect, then it is Y1 into t plus 1 is equal to alpha into 1 minus s into 1 minus lambda multiplied by yn plus lambda Y0 in the t generation. In that way, for the then offspring with R defect, that equation is written in equation 11. So now when the fractions YR vary slowly from generation to generation, okay, so we can also write this equation. So this is very simple again because this I have written earlier also. So YR into t plus 1 is equal to YRT plus dyr by dt simply. So this red term only I have included here, and now we can write this equation 12 in the differential equation in the form that dy0 by dt equal to alpha into 1 minus lambda minus 1 Y0 y1 by dt is equal to alpha lambda Y0 plus this term, and in that way dyr by dt equal to represent that is equation 15. Now the above differential equations are to be solved subject to the boundary conditions Y0 equal to 1, YR equal to 0. Okay, so these are the boundary conditions for R equal to 1 to n at time t equal to 0. So now as the normalization factor alpha is a function of time according to equation 8, we evidently have a set of nonlinear equations. So if alpha becomes the function of time, then it will be nonlinear equation, and we evidently ultimately we are having a set of nonlinear equations for determining the flow of harm mutations in the succeeding generations. So initially for alpha equal to 1, the coefficient Y0 on the right side of equation 13 is minus lambda, hence Y0 declines initially. So if you just look into the equation, you can get now equation 14. Okay, this is the upswing with the single this defect because of the alpha lambda y0, this term, this alpha lambda y0, because of this term on the right side of the equation 14, y1 at first increasing but is then checked by this term minus alpha into 1 minus lambda into 1 minus s minus 1 multiplied by y1. So this term, okay, so this term, and thus y1 rises at first, then attains a maximum and thereafter falls away to lower value, and as time goes on y2 y3 and yr show a similar behavior. Therefore we can observe from these points that initially this defect is increasing, okay, defect is increasing, but after some time this it is being checked, or it is being restricted by some factor, and that factor is this one here, and this is for all the offspring with 2 defects, 3 defects, and with R defect. And in that way, if we plot the time plot for y0, that would show a curve that declines steeply at first, and the levels out to some ultimate value, say y0, while time plots for y1, y2 are curves that rise initially from 0 to maxima and then fall away and level out at ultimate values. Those are y1 bar, y2 bar, okay. And our problem is to calculate these ultimate values, that up to what extent this deleterious mutation can happen, or up to which level actually the bad mutation will or the harmful mutation will continue to flow. So this is our objective, and in the what is those ultimate values, okay. So in order to calculate that, so from equation 13 to 15, we can actually, in order to calculate y0, y1, yr, if we directly take their differential 0, and we can calculate, but it is not so simple, because here the equations and unknowns are not same, okay. So, and we know that when the number of equations and the number of unknowns are same, we can get unique solution in any mathematical system. And when the number of equations are less, we cannot solve as compared to the unknowns. And when number of equations are more as compared to the number of unknowns, then we cannot have the unique solution, okay. So please remember, when number of equations are more as compared to the number of unknowns, we cannot have unique solution. And in order to bring that unique solution, we have to we have to bring certain more involved steps, and that I'm now trying to bring out. Okay, so each solution for y0 bar, y1 bar, this is characterized by an integer, suppose q, such that a coefficient in one of the equations becomes 0, and therefore this alpha bar into 1 minus lambda into 1 minus s to the power q minus 1 is equal to 0, and where alpha bar is given by this, this is in a similar spirit only, one can look into the solutions for y1 bar, y2 bar is then r bar is equal to 0 if r is less than q, and for r greater than q, the recurrence relation 20 is obtained. So, and with this equation for r equal to q to q plus r, in that way q plus 1, so one will complete the solution. And in case this q equal to 0, then equation 17 gives alpha bar into 1 minus lambda equal to 1, and using 20 in equation 20, yeah, will yield yr bar, that is maximum defect, okay, maximum value of the defect when there is in offspring with R defect. So maximum bad mutation actually. So that is equal to lambda by 1 minus lambda 1 plus s 1 minus s to the power r minus 1 by 1 minus s to the power r multiplied by y bar r minus 1. So I know that I'm running out of time. It is 4:44, but please allow me some 6-7 minutes so that I can complete.
Yes, sir. You have about 6 minutes, sir.
Okay. So for s very less than 1, the above equation can be rewritten as okay. So if one can work with this equation, one can get easily a similar treatment for q not equal to 0 its equation 24 to y r bar is the lambda by 1 minus lambda into 1 by e to the power r minus q s minus 1 multiplied by y bar for r minus 1. And from this observation, we can see that the case q equal to 0 is going to be the best one from a biological point of view, because it is permitting the least penetration to the defects into the population. Okay. So therefore, now with q equal to 0, we have the solutions for y1 bar, y2 bar, y3 bar in that way, and hence equation 21 will be yielding to this y0 bar within the bracket 1 plus this lambda by 1 minus lambda s, and in that way if one writes then you will get it is equal to 1. And for this r less than 1 by s, the terms of the series are as given in equation 29, namely the terms in the expansion of this e to the power lambda by 1 minus lambda times s, making an approximation adequately. We have that y r bar is equal to 1 by factorial r, this lambda by 1 minus lambda times s to the power r e to the power minus lambda by 1 minus lambda times s. And this above equation is just the Poisson distribution. If anybody knows, one can get, one can for average value lambda by 1 minus lambda into s, and this is the number of defects possessed by an average number of the population, giving a reduction of fitness by this, which is equal to your e to the power minus lambda. And it is worthwhile to mention that terms of order lambda square were omitted already in the differential equations 13 to 15. So one can refer the result. Equation 31 is analogous to one obtained long ago by this Handane for a bisexual reproduction. So this is one actually check or one validation. And the q not equal to 0 in a similar way will be yielding to produce the yr bar is equal to 1 minus r minus q factorial, and this lambda by 1 minus lambda s to the power r minus q e to the power minus lambda by 1 minus lambda s. And writing r equal to now q plus k, we have y0 equal to y0 bar equal to y1 bar equal to, so these are the maximum values of the bad mutation flowing in generation to generation, and from upstream to upstream, sorry, equal to 0. And then y bar q plus k will be giving this 1 by k factorial this term, and this parameter q simply changes the 0 point from which the number of defects is counted with q equal to 0, the least bad situation for the species. The boundary condition equation 16 defined y0 bar as the first non-zero function requiring 0 point q equal to 0 if the boundary condition had been y0 equal to y1 equal to 0, y2 equal to 1. In that way, that y3 equal to y4 equal to 0, y2 would have been the first non-zero fraction, and q equal to 2 would have been the appropriate 0 point. Now the natural selection is able to prevent a situation in which average individual has a fitness lowered by e to the power minus lambda from worsening any further. However, it cannot prevent the original situation from worsening, and therefore this y bar we are having yr bar we are having 1 by r delta lambda by s to the power r e to the power lambda by s. And with this distribution, and if no further deleterious mutations were occurring, the average number of defects in the next generation would be given by this equation 35. And here the implication of okay, just let me tell the points, then I will tell you further more on this. So instead of each generation transmitting its own average lambda by s of defects to the next generation, selection in the absence of new mutations operates to reduce the number by lambda, which of course is just compensated by the new mutation rate. Once the YR values have evolved according to our differential equations to give the Poisson's distribution 34, okay, 34, the situation is held in balance from generation to generation by natural selection. Okay, so therefore I have to say that this natural selection actually initially cannot support the evolution theory, but when after a statistically distributed defects in the upstream is generated, then only this evolution theory may come into a picture. So therefore, in order to conclude, so I must state these points, like this natural selection is not a promoter of what is good in any absolute sense. Natural selection can only favor what is better against what is worse. The natural selection is able to prevent a situation in which the average individual has a fitness lowered by e to the power minus delta from worsening any further. However, it cannot prevent the original situation from worsening. The logic is that in the original situation with y0 equal to 1, natural selection had nothing to operate on. Every population member was equal with nothing to choose between them. So therefore, until and unless this statistically distributed defects are not, or bad mutations are not being generated in the upstream, so natural selection does not have any place to act. And only after mutations had produced a statistical distribution of defects represented by the Poisson distribution with average value lambda by 1 minus lambda into S, there was a sufficient separation between lucky and unlucky individuals for natural selection to hold the position from further decay. So I'm not before that. So please remember this point, because this is the main striking point in the model, that until and unless this upstream is generating a sufficient number of bad new mutations, so this natural selection theory cannot act, and therefore it prevents an inseparable problem. But the notion that life arose out of an biological organic soup through the development of a primitive replicating system, and a primitive replicating system could not have copied itself with anything like the fidelity of present systems. With only poor copying fidelity, a primitive system could carry little genetic information without becoming unbearably large, and how a primitive system could then improve its fidelity and also evolve into a sexual system with crossover. This is very, very difficult and unimaginable. And this presentation I am dedicating to my spiritual master, Dr. T.D. Singh, and therefore I should read this. I'm extremely indebted to Dr. T.D. Singh, because of whom I got the platform to work on such a foundational and exciting topic. So with this, I'm stopping. So now you may ask the question, and for which I will try to answer.
Thank you so much, Dr. Debashis Khan, for your intriguing presentation on the mathematics on the origin of life. So now we'd like to open the floor for questions from the participants. Maybe we can unshare the screen, and you can raise your hands, please, so that we can call upon you. Just give me a second. Can we have Professor Debashis Khan on screen, please? Okay, great. Okay, we have a question from Niket Kumar Shah. Can you unmute yourself?
Yes, sir. Can you hear me?
Yes,
Yeah.
Go ahead.
Yes, my question is like you have written so many equations like y equal lambda by 1 minus lambda mod s whole power r minus s, then exponential minus lambda by 1 minus lambda mod s like this, and then some recursive equations also you have written like yrt plus 1 is yrt plus d by dt yrt. But all these equations has some basic assumption like it is Poisson distribution, and that too like mod x is very less when compared to 1, like very small population has been considered to have some defect, like 1 out of million you have also given example. But like mutations sometimes don't follow this very small thing, no, like it can be random also. Like you have told the last point that cross coupling reproduction happens which may favor the fittest one, like Darwin's theory also. um, but the point is like sometimes organisms are adapting themselves for a new thing also, like nature favors only like opposite gender to like each other. But now sometimes like some evaluation is also happening in this, like then how these changes happen, and like so many population get affected, or what is the exact modeling in this last point of cross coupling uh, theory in that
Okay.
lambda by 1 minus lambda into mod s.
Okay, Niket. Actually,
Yes.
this has been made for a very simple system, please, for asexual reproduction system. And yes, you are correct in the sense that there are some idealizations, but this has been actually it has been this model has been made to show that at least that whether this natural selection theory is correct or not, or up to what extent it is correct. But one can modify it for the new system, this new mechanism, or if you are making some changes in the data, you can test with that also. But okay, so you are encouraged to do that experiment, and you come out and bring that what new information you are getting that in the natural selection.
Yes, sir. Like mutation happening in organism, like which is not favored by nature. Also, things are happening. Like
Yeah,
individuals are having some different kind of lives also, but nature favors only like means different gender lives, means some kind of like unnatural phenomenon also is seen in population. Is it random or like how it is happening? How it follows, and means then X also
Let's keep it to one
correct in
question at
that.
a time, please. Just one question at a time. Can you just address that question, sir?
yeah. So
Yes,
the same thing I'm
yes, sir.
repeating again, that
Yes.
this has been made for this basic model, and once you change the data, you can test. But the method, actually same method you can keep, and with changing in your data, you can test the model that to what extent this is working.
Okay, thank you.
Thank you, Nikit, for your
Yes,
question.
sir. Thank you for answering my question.
We now have maybe Dr. Jayanti Chavan to please ask your question. Can you please unmute yourself? Dr. Jayanti?
Yes, I was not able to unmute. Okay. Thank you, sir, for your wonderful presentation. I just want to know now this Darwin's natural selection, you said it is corrected in limited sense. So from your study, does it highlight the favorable mutations are true in the sense that it does not install new features in organism? Because Michael Behe has definitely said about this, that new features cannot be installed in organism, that is macroevolution take place. But what happens at the micro level is there is a reference to trait, change of color, height, and those things. So that is what you meant, that natural selection is correct in limited sense.
Yeah,
Could you?
yeah, 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 yeah.
That's it. Okay. That means it is not going to install new features,
No,
right?
no, 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 no,
Okay.
at all. Even
Okay.
even sometimes a theory is working in a limited sense. That does not mean that this theory is correct. It may be wrong also.
Yes. Okay. Thank you. Yeah.
Okay. Maybe I could afford a question now. When you talk about defects, are you talking about defects which are visible externally, or you're also referring to defects which might be developing internally in the organism?
Uh, it may be both. It may be both. But some changes in the gene actually that harm that on that level you please consider. that harmful mutation means that deleterious mutation, and therefore actually so it is within the cell. You can consider it is not externally.
Okay. Are there examples of a positive mutation that you can maybe share with all of us? Good mutations that you talked about.
So my equations are not actually written on that way, but I have considered that this is good mutation, this is bad mutation, and I have marked with them with certain actually parameters, and on those basis actually I have done it. So what is good? So that one can look into. That one can look into.
Okay. So are there any more questions for Dr. Debashis Khan before we close this session? Okay, Niket, you just have to leave it to one small question. Okay, we've got 1 minute. Okay, for that, Niket, you can lower your hand, lower your and then unmute yourself and ask that one question.
Yes, sir. Actually, my question is like Darwin's natural selection theory was means contradicted also, no, in step one, Fred Hoyle's theory. Can you explain like how that natural selection has been contradicted?
Okay.
Yes, sir.
Thank you.
So it is step one where I have told that if any property is favorable, so ultimately in that population only those favorable properties will be existing, nothing harmful properties will be there. But at the same time, if there is any harmful property, so in due course of time only harmful properties will be there. But with the values of s, actually that small s I have shown. So but it does not happen in our this in the population generation after generation, because we see that generation after generation we have some stable population in any species. We can observe that it is not that suddenly everything is eliminated or suddenly everything is there. So every time some bad, some good these properties are existing. So on the basis of that, this first thing is discarded.
Yes, sir. Thank you, sir, for your presentation, and I understood. Thank you for taking the question.
Thank you so much, Dr. Debashis Khan, for your presentation and for the discussion, and thank you all for your questions.
Thank you so much.